What's going on, Google Play Store? Welcome back to Chemistry. Anyhow, let's get to the first question. A thin sheet of metal is to be plated with copper, which has a density of 8.96 grams per cubic centimeters. The area of one side of the metal sheet is 400 square centimeters, while the thickness of the copper plating should be 1.00 times 10 to the negative 2 centimeters. The process produces copper 2 ions. Yes. If the current flowing through the electrolytic fluid which initiates the process is 3.00 amperes, how long will it be until both sides of the metal is covered with copper? Now, what does a thin sheet of metal plated with copper look like? It should look like a bit like this. Hold on. So it should look a little bit like this. This is the thin sheet of metal, for example. And then we need both the surfaces to be covered in a small copper plating, example maybe like that, of copper, So this is copper, but both sides. So there are two sides here. The area of one side, or the surface area of one side, is 400 square centimeters. You multiply it by 2 to get two sides, you get 800 square centimeters. Now, the thickness of the copper plating, they said, is 1.00 times 10 to the negative 2 centimeters, or 0.01 centimeters. So we multiply 800 square centimeters by 0.01 centimeters. We get a volume, which is going to be, let me just calculate it, 8 cubic centimeters. This is our volume. We have a volume. Let's try finding the mass of everything. So we have 8.96 grams per cubic centimeters, and we get 8 cubic centimeters. We can cancel the cubic centimeters in here, and then we can multiply 8.96 by 8. We get 68 grams. Now, hold on. So the next step is to take the grams and then transform it into moles. So how do you transform it into moles? Well, you have to look in the periodic table to get the molar mass of copper, and a quick search of it. The molar mass of copper is around 63.54. Yes, 63.55 grams per mole. We have to convert that into mole. We have to convert 71.68 grams. So how do we do that? Well, first we set up the mass of the copper we have. We multiply this by 1 mole here, and then 63.55 grams here. The grams should cancel itself out, leaving us with a mole, and 71.68 divided by 63.55 results us in 1.128 mole. That is our important numbers. Don't forget them. So we have 1.128 mole of copper. So what do we do with this? Well, we find the half reaction of the electrolytic reaction first. So the half reaction should be copper, and then they say it's 2 plus, so 2 plus ions. Then we add 2 electrons here in order to get copper. So for 1 mole of copper, this is equivalent to 2 moles of electrons. So we can equate 1.128 mole of copper, and then we multiply that by the by how this is equated. So 2 mole electrons per 1 mole of copper. Mole copper, they cancel each other out, leaving us with 1.128 times 2 moles of copper. We get 2.256 moles of electrons. This is how many electrons flow through the metal. So we have 2.256 moles of electrons. We have this constant, which is Faraday's constant actually, that states that we can multiply this by 96,485 coulombs per 1 mole of electrons. This is the conversion factor of mole electrons to coulombs. So we can cancel mole electrons out. We get that 2.256 times 96,485 coulombs is equal to 217,670.16 coulombs. We know Q equals IT, and we already have I, we already have Q. What we're finding is T. So let's isolate T. T is equals to Q over I. Our Q is 217,670.16 coulombs divided by 3 amperes. The answer here would be 72,556.72 seconds. In minutes, that would be 1209.279 minutes. In hours, it's still too big. So in hours, this would be 20.15 hours. That is the answer. Usually you wanted a nice number, so in hours that would be better. But it depends on what the question is asking, of course. All right, next question. Number 2. The following is a reaction taking place within an electrochemical cell. A solid zinc plus aqueous copper ions, which is 0.20 molars, is the reaction, and then aqueous zinc ions, which is 0.40 molars, plus solid copper, or metallic copper. The standard reduction potential of the associated reactions are the following, and then the question is, what is the non-standard electrode potential E cell if the temperature of the environment is 300 Kelvin? Now this is not standard, this is non-standard. So we have to use the Nernst equation, which is this. This is the Nernst equation. And we have to use everything in here to find it. So we can't use the other one. There's another Nernst equation, which is E cell equals E standard cell minus 0.0592 over N, and then log base 10 of Q. We cannot use that because the temperature is not standard. The temperature is 300 Kelvin instead of 298 Kelvin, which can be used here. So this is used only when standard only when standard environment conditions, whatever. So we have to use this Nernst equation. So how do we do it? Well, we have to start by completing this reaction using these two right here. So what do we have to flip in order to do this? Well, the copper is in the right place. Yes, but the zinc is not in the right place. We have to flip zinc. So let's flip zinc. So we get zinc goes to zinc 2 plus 2 electrons. Now, since this is negative, since we flipped the switch, we have to put we have to make this negative. So negative of negative 0.41 volts is just positive. So the standard E is 0.41 volts. This is the standard electrode potential of that reaction. We don't have to change anything after this. So copper is already okay here. uh Copper solid, copper, yeah. And the E is 0.34 volts. Now we just have to add this, the SRPs. These are both SRP, so we have to both add this. We get 0.41 plus 0.34. We get 0.75 volts. This is the standard electrode cell potential of the reaction of zinc plus copper, which is going to be zinc plus copper, and then the electrons cancel each other out, so it's okay. So 0.75 is our E cell, so that's going to be very important. E standard cell is 0.75, but we want non-standard. This is still standard, so we have to use the Nernst equation, which is again right here. So how many electrons are transferred? Well, there are 2 electrons transferred here, so N equals 2 immediately. The temperature is 300 Kelvin, which we don't have to put any conversions in because it's in Kelvin, so that's fine. And then the ideal gas constant is this. This is R, and this is Faraday's constant. Alright. So the gang sol here, we just calculate E cell right now. E standard cell minus RT ln Q over NF. But wait, what's Q? Q is equals to basically this. Zinc 2 plus, which is the in the reaction product side, multiplied. The power is just 1, so we don't have to worry about anything. So copper, and then the power is 1 over zinc solid. The power is again 1. Then copper 2 plus ions, so 1. So the Q here is equals to for the zinc plus, we get 0.40 molars multiplied by 1 molar. There's no molars attached in here, so we just assume this is 1 molar. Same with here. This is 1 mol. We just assume this is 1 molar. Divided by the zinc here is 1 molar multiplied by 0.20 molars. This is going to be 2. That's the Q, which is the reaction constant or the reaction quotient. We have everything now. So we have N, we have F, we have T, we have R, we have Q. So, and we have E standard cell. So let's find E cell. So this is 0.75 minus R, which is 8.314 joules per mole Kelvin, multiplied by the temperature, which is going to be 300 Kelvin, divided by, we multiply by ln of 2, multiplied by N, which is going to 2, and then by Faraday's number, which is going to be 96,485 joules per mole Kelvin. Joules and joules cancel out. Moles, no, not moles Kelvin, moles voltage. Okay, moles and moles cancel out. The Kelvin and this Kelvin cancel out. There's no unit here. And for the voltage, this goes up, up. So this is in terms of voltage. So let's try finding the E cell using the calculators at hand. You should have calculators here because you cannot do this by hand. Please don't try doing this by hand. It will hurt your hand. 8.314 times, hold on, 0.75 minus 8.314 times 300 times ln2 divided by 2 ln2 divided by 2 multiplied by 96,485, and parentheses, we get around 0.70. How many significant figures we have? It's 2 significant figures, so it's around 0.70 0.74 volts. That's our non-standard set. That's nice. All right, that's the answer. All right. The next question is related to this a bit, which is for number two, what is the Gibbs free energy of the reaction? Is it spontaneous? Uh, let's go back to the reaction. This is the reaction. Uh, Hold on. This is the reaction. What we're trying to find is the delta G, which is the Gibbs free energy, the non-standard Gibbs free energy. So we have the E cell. We have E cell right here, which is going to be 0.74. So we know. Hold on. We know that the E cell is equals to 0.74 volts. Faraday's number is, oh sorry, wait, the formula is wrong. This should be a negative. I'll correct it in the file. The Faraday's is 96,485 joules per mole voltage, and the number of electrons is around, well, 2 moles. All right. So what do? We just multiply it together. The delta G is equals to negative NFE cell. And then this is just going to be negative of 0.74 volts times 96,485 joules per mole voltage multiplied by 2 mole electrons. This is mole electrons. This cancels. The volts cancel out. So we are stuck with joules. So do a negative 0.74 times 96,485 times 2. Our Gibbs free energy is negative 1.4 times 10 to the 5 joules. Now, remember to the thermochemistry that we had. If the enthalpy is negative, it releases heat, right? And then if delta H is positive, it absorbs heat. In Gibbs free energy, it's the similar train of thought. If G is less than 0, and then it releases heat during reaction. So what happens is that the chemical reaction releases heat. Therefore, the chemical reaction is actually being done. So it is spontaneous. If delta G is positive, it absorbs heat during the reaction. What does that mean? Well, during the reaction, it needs heat in order to react. It needs heat. There are reactions that actually absorb heat that are spontaneous, but this one, it needs the heat in order to react. Kind of like melting ice is a chemical reaction, but you need heat in order to melt the ice. So that is something that is heat. For example, maybe a boiling water actually is a much better example of that. So if you try boiling water at room temperature, you're not gonna have any luck because it's not spontaneous. But if you boil heat at like 100 degrees Celsius, that's good because you're adding heat onto it. So it's going to it's going to react, boil, So this is negative. So we just say this is spontaneous. That's it. And on to the next question. Number 4. A certain radioactive material initially decays at a rate of 2 times 10 to the 5 disintegrations per minute. After 4 days, this decay slows down to 9 times 10 to the 4 disintegrations per minute. What would the decay rate 40 days after the initial measurement be? This formula, A of t is equals to A of 0 e to the negative kt, where everything, So let's examine the formula first. A of t is equals to A of 0 e to the negative kt. The A of t, this is mass. So this should also be mass, since a of 0 is just when t is equals to 0, time 0. So mass at time t. Alright? This is mass at time t. Then, again, this is going to be time. So what's the unit of k? Well, the unit of k is going to be 1 over time. So whatever time is, it's going to be the inverse of that. Or we could write this as time to the power negative 1, inverse time. So let's put the relevant units around here. This is going to be particles. All right, this is going to be particles as well. And you'll see why in a short while. Why is it is particles, not grams or whatever. So t is going to be in days, and k is going to be in inverse days, or 1 over days. So that's going to be our units. Now, our decay given is the decay, which is disintegrations per minute, which is disintegration. What is disintegration? So you can think of a disintegration as the loss of one particle. So it's negative 1 particle. So one disintegration is negative 1 particle. It will lose 1 particle from the radioactive material. So that's going to be our unit. So disintegration, then we put minute here. Is particle per negative 1 particle per minute. So we're going to be using the units later on. So how do we transform from particles to particles per minute? What process can we do? There's a hint here. Rate of change. Disintegrations per minute is the rate of change. And when I hear rate of change as a mathematician, wow, I hear derivatives. So let's try finding the derivative of this function. A prime of t. What is a prime of t? So this is going to be the derivative of a with respect to t. Alright? So this is going to be, a of 0 is just a constant. So just put it here. This is a constant of the mass when t is equals to 0. And then e to the negative kt. It remains the same since the derivative of e to the x is just e to the x. And then we multiply this by negative k. Rearranging, we get negative a of 0 k e to the negative kt. This is suspiciously hold on. This is suspicious because this is particles. This is going to be 1 over day. The negative particles per day, or negative disintegrations per day. So close to disintegrations per minute. So what can we do? What can we do in order to match this? Because the unit of this is disintegrations per day. Well, what we can do is to say and then just put that there, right? And then e to the negative kt. So what is delta? Delta is just the decay at time 0. Alright? Because that's what we transformed a0 e to negative a0k to be. What's the unit of lambda? The unit of lambda is anything you want, as long as it is mass or depletion of mass over time. That's all it is. So this can be disintegrations per minute. Alright? It doesn't have to be per day. It can be per minute. So good. So using this formula, we can find the disintegration rate of after 40 days. But we need to find the value of k first. What is k? Well, we can find k here. We know a prime of 4. What is a prime of 4? Well, that is at t equals 4. Right? So the decay is said to be 9 times 10 to the 4 disintegrations per minute. And lambda should be the decay. Again, this is the decay at time t equals 0. So this is going to be 2 times 10 to the 5 disintegrations per minute. Since that is the disintegration initially, time equals 0. So e to the negative k, then we multiply it by 4 days. So we just need to find what k is. Then let's isolate k first. K is equals to, after a little bit of algebra, this becomes negative 1 over 4, the natural logarithm of 9 times 10 to the 4 over 2 times 10 to the 5. This integration, oh no, no units inside. So this per min over this integrations per minute. So what happens here, the disintegrations per minute cancel each other out, so we're left with that. So let's find the k for this one. So negative 1 divided by 4 natural logarithm of fraction 9 times 10 to the 4 divided by 2 times 10 to the e5. Our answer is 0.199627 inverse days. So we need to have lots of decimal points in order to get our point across, because this is going to be extremely precise. So that is k. So k is equals to 0.199627 inverse day. And our formula now is a prime of t is equals to lambda e to the negative kt, where again lambda is the decay at t equals 0. Alright, so we know k, we know t, which is 40. So we just need to we just need to calculate a prime of 40. A prime of 40, this is now equal to lambda, which is the initial. The initial is 2 times 10 to the 5 disintegrations per minute, multiplied by e to the negative, what is k? 0.199627 inverse day, multiplied by 40 days. So inverse day and day cancel each other out, leaving us with the unit disintegrations per minute. So let's calculate the disintegrations per minute. Then we multiply this by e to the negative 0.199627 times 40. So we are left with the answer 68.101 disintegrations per minute. And guys, that is the answer. If you took that on a quest and the answer is kind of familiar, I shifted the power 1 less, so it's a little bit different. But I got that from that quiz, for the people who are familiar with me. But anyway, let's move on to the final question. Question number 5. The half-life of titanium 44 is 60 years. How long would a 100 gram of sample of titanium 44 decay into 8.43 grams? This is the given formula, similar to last time, but we're not going to do any derivative situation here. So what we're going to do is just to apply that. Easy enough. We're trying to find the time. So let's try isolating time first and before doing anything. A of t is equals to a of 0 e to the negative kt. We need to isolate this thing first. So let's divide both sides by a of 0. Yes. So negative e to the kt. So we can find the ln of both sides to remove this situation with the ln with the e here. So ln and e cancel each other out. So we are left with negative kt is equals to ln of a of t over a of 0. Good. So in order to isolate t, we multiply both sides by negative 1 over k, so we can cancel that one and we can cancel that one. So we are left with negative 1 over k natural logarithm of a of t over a of 0, which is going to be what we're going to use today. So what would so we need the time for this, so let's try finding it. First we need to find what k is. K should be ln2 over the time, the half-life, which is going to be 60 years, and this is equal to ln2 divided by 60. This is 0.0116 inverse years. So, negative 1 over 0.0116 inverse years, and then ln of 80, which is going to be 8.43 grams. This is the amount of material after time has passed. Then A of 0, which is the initial 100 grams. And plugging that into the calculator as we do, multiply by ln of 8.43 divided by 100. The answer is going to be 213.22. What's the unit? Well, year on the inverse year on the bottom is year on the top. So the unit is going to be year. Again, we just put that on top. So the unit is going to be year. So the time it takes for the sample to decay is going to be 213.22 years. And that is all for now. I'll see you later.